Yeah, any decimal answer, unless it is, you are told specifically to not go to 3 decimal places. So now this was 750 something. We said you didn't have to round, you could truncate. So if it was 4750 and you leave off the 0, we can assume a 0 and you can get away with it. But I wouldn't, I mean, I just always 3 decimal places. So writing this out was a point, getting that answer was a point. Then you were supposed to evaluate it with the fundamental theorem of calculus. So now you do the antiderivative. You have to show this. When it says use the fundamental theorem of calculus, that means big F of B minus big F of A, which means big F is the antiderivative. You've got to write out the antiderivative. You can't just write big F of B minus big F of A, because then you can just type that in your calculator and get the answer. You've got to write out the antiderivative, do your right bracket, and then you plug in, and you could have left it like that or like that. I mean, when you type in your calculator, if it gives it to you like that, just give that answer. Don't worry about going to a decimal. I mean, you can give a decimal, but then you got to make sure you get 3 decimal places. Just give that answer. That's fine. Okay. All right, next one. We had a similar one in the homework, so that was probably a good thing. You would have had that one because this was minutes and miles per hour, so it would be kind of silly in 10 minutes, even though you do go 100 and some miles an hour, in 10 minutes it would be hard to go 696 miles in 10 minutes. You'd really be moving, right? You go 11.6 miles. You got to divide that by 60. I kind of wrote it out the way kind of Will had said that day. Can we take these times 2, each of those times 2? And so I kind of did that. I did the width, B minus A over N, and then I got my 1/2 in there too. So 10 minus 0 divided by 10. So it'd be 1 wide. Each of them is 1 wide, but then you got to have a 1/2 out there. So that was 4 points. This one was 4 points, and that was, I kind of had a point for writing it out, but to be honest, to go from here to here, you don't have to write it out, so it wasn't necessary that you do that. The integral goes from 0 to 8. It has to, because when you put your 0 in here, these would be left rectangles, so you put your 0 in here, you get e to the 0. Well, that's your left edge. That should be your left edge. It should be 0 when they're left rectangles, and the 2/5 just disappears, and then you have 19. You put 19 in there, that'd be 38/5. Well, that's going to be 1 width short of the right edge. So 38/5, the width is 2/5, that'd be 40/5 would be the right edge, which would be 8, so 0 to 8. Or you have 20 rectangles, 2/5 times 20 is 8, 40/5. So 0 to 8, and then the antiderivative is e to the x, so e to the 8 minus e to the 0. But here's the thing, here's where I could believe how many people did this. How many people had this? And if you had, this is where I got lenient. If you had this, why write anything else? Just stop, right? Just stop. But some of you wrote 2979.96, and I'm like, why are they doing this? It was driving me crazy. I couldn't believe how many people were doing it. Because it doesn't round. I mean, it would be 958 or 959 maybe, but it would not round to 96. Okay, and so you've got to do 3 decimal places. Okay, so that is not good. But then what I did was, well, okay, if you had that, I went ahead and accept that. But if you have this, which is correct, and then you go to a decimal and you do not do 3 decimal places, you will lose that. You will not get that answer right on the AP test. Okay, they're pretty plain about that, about doing it. Okay, backside. But other than that, we did really well. I mean, it was, I don't think, I tried to be honest, I kept things pretty basic, I think, on here. So, what we worked on. So 2 pi8s or pi4, so either one of these. So f of, so I kind of didn't write the f notation, but somebody forgot the sign or to plug it into the function. But sine of that, I equals 1 to 8 with that here. Okay, then you just had to distribute this and then use your 2 formulas to get your sum right there. So that was 2 points. So I squared plus 2i. Those formulas were at the top of the page. This was an interesting one. So this was, I kind of wrote it backwards, seeing if that would throw some people off. But So there were a number of you who did that, but some of you just figured out, oh, it's the same as if you just flip it around. It's just 1 squared plus 2 squared plus 3 squared. Doesn't have to be in that order because it's adding, so you could just do I equals sigma I squared 1 to 10. But, and then a lot of people did 0 to 9. A lot of people went I equals 0 to 9 and went 10 minus I squared like that too. So that's fine. And then this last one's worth 4 points, and basically you had to get these features in there. I needed to see, it was amazing. Some people wrote this whole big thing and never once used the word area. Okay, you got to get area in there somewhere. You talked about height or width, or didn't use the word rectangle, right? You got the word rectangle and area better be in there. So, you know, people talk about height and width, but height and width of what? And then the fact when you multiply those, you get area. There are 4 main parts to this. This is a rectangle area because that's a height and a width. This is adding them up, and this is telling you that you have an infinite number of them. So the height of a rectangle, width of a rectangle, making area, adding, and then you're adding up an infinite number of them. Okay, and then that's why that represents. I think I changed the wording on this. This says area under the curve. I think it says the definite interval, right? I changed the wording on this since I had this key, but this is not same. Okay, all right. All right, so let's take a look at the tabular reasoning worksheet first. All right, what questions do you, which ones do you want to ask about on that? On that one. At this point in time, I would say there are 2 really important, well, I don't know about 2 really important, maybe more than that. Several important. Why don't you get your notes out? Let's jot this down right now. Oh, by the way, on the gateway test, you may have noticed I put in your best score just in case that's what you were planning to do. I don't know, some of you haven't taken another one, some of you had. Now, at this point, about the only way to retake is to come in before school, Bearcat time, or 4th block, right? Now, if you had first block, well, you don't have first block, obviously. So, 4th block, when I'm available, and before school, Bearcat time. Okay, because after school, track practice isn't going to work really. So those would be the times to come in, and if you're going to do it before school, you probably want to get here by about 7:15 or so at the latest, probably. Make sure you have time, 7:20 maybe, whatever, because you have to be done before we start class. All right, so anyway, so I put those in. So if your best score is a 5, so I put in a 15 out of 30, okay? Because the end of the term is coming up this week, and so we need to get those done. So if you want to keep trying, so right now, if you remember your second, if you take number 2 and number 3 and you pass those, that's a 27 out of 30. Number 4, number 5, pass one of those, that's a 24 out of 30. And then at that point, if you've already got a 7, that's 21 out of 30, and that's the best you can do once you get to number 6 anyway. So if you've gotten a 7 by then. So anyway, that's in there. And if you just are planning to leave that as your grade, that's fine. All right. So at this point, applications of the definite integral. Okay, what do we have? Well, one thing that we have is average value of f of x. Okay, so we have the integral of a function divided by, right? And sometimes that's written 1 over b minus a times the integral, right? So the average value of a function, okay? And then I guess I should back up one here and just remind you, you don't need to write this down, but when we have a definite integral, right, we have 3 different ways we can do that. We can either do it with geometry, which is hardly ever the way we do it. This, or what's the last one? Approximation, which would be lefts, rights, midpoints, trapezoids, right? Now these two calculator will do either one. Remember when I showed you that? I've shown you that in the past, where if it's a calculator problem, we can just type in. I mean, maybe I should add that as a 4th one, right? It's not really a 4th one, but when you're doing it on the calculator is going to choose. The calculator is going to choose which one of those 2 it's going to do. Okay. So when we go to, so we talked about this here. So if you're going to do, if you want to find right, the calculator is going to use the fundamental theorem to find it. Okay. Now, if you take that same problem and you change that to x squared, right? Now the calculator is going to do an approximation technique because there is no antiderivative to this. Okay. So what I'm talking to you about here is setting up. How do you set up an integral? Okay, to do these various problems, because that's a lot of what we're going to get into here. Well, mostly in chapter 7. We have to go through chapter 6. It's a fairly short chapter. We're going to go through that this week and into next week and do one quiz on chapter 6. And you're going to have another assignment. We're going to talk about being basically your first assignment quiz from term 4, because the term ends this week. So about the only other grade we have from the term to go in there is a daily grade, is a homework grade here that we've been working on. But so anyway, right? This we're going to be going into applications of the definite integral, and you're going to have to get a proper integral set up. And that's a lot of the work. Once we get the proper integral set up, then we have to evaluate it. Matter of fact, there are some problems on the AP test where they just say set up the integral but don't evaluate it. Don't worry about it, right? Especially in the no calculator part, sometimes looks good. So we want to get the proper integral set up, and then how do we evaluate it? Well, 90% of the time we just type in our calculator, right? We will get to do that a lot. We'll get to type in, we just type in our calculator, because the whole point is, did you get a proper integral set up? Okay, but other times they'll say, use 10 left rectangles to find the average value. So that was kind of my point here, is the problem might be an average value problem, and that's what you have in the table. You know, it might say, find the average value by setting up 10 left rectangles or 6 trapezoids or whatever. You're not using trapezoids to find the average value. You're using trapezoids to find the definite integral, right? The trapezoids do this part, and then you divide by that to find the average value. Okay, so important to understand. Okay, that's number one. Number two. Okay, so application of definite integral. So one is finding the average value of the function. Obviously, one is finding the area under the curve. I mean, that's what the definite integral was, right? So finding the area under the curve, that is clearly an application of the definite integral. It's so obvious, I'm not going to write it down. Okay, this one, the generic one would be this: the integral of a rate of change is what? What does that give you? Close, not total. We don't use the word total. The net amount of change. Okay? Now let's get some examples of that. Okay? So if this was the integral of miles per hour, 0 to 3 hours, let's say. Say that was dt, probably hours. What would that give us? Miles. It would give us miles, but more than that. I mean, we need to be more specific than that. Net distance traveled in 3 hours in miles. The units would be miles, that's right, but that would be the net distance traveled. Okay, it would be like saying, if this was, let's say this function in here was x prime of t, then this would be like saying x of 3 minus x of 0, right? Because that's the antiderivative, right? X prime would be, so we got something moving on the x-axis. A lot of times we've used x as that function. X prime, let's say, is miles per hour. So the antiderivative, fundamental theorem part 2, would tell us find the antiderivative, which would be x of 3 minus x 0. Well, this is just where it is. This is its position at the end minus its position at the beginning. So that's a net distance that it traveled. Net distance, like displacement. Okay? So that is what you'd be finding. So we don't want to say total. The only time that net and total would be the same if what? When would net and total be the same? No? Think about it. Because it's going to give you this. It's going to give your ending position minus your starting position. That's your net distance traveled. So if I go this way, and I come back this way, I'm always going one direction. Not just right, though. I could just be going left, too. That would be the net. That would be the total distance traveled, right? If I was going backwards, right, when you subtract it. Now, it might be negative, right? So so total distance, you might do the absolute value. Now, okay, I'll get to that in the next page where we can do total, okay? Here's another example, though, that sometimes people don't think about. Well, wait, let's do 2 more examples. Squeeze this in. Okay, let's say we had, this is one that sometimes people don't think about. Let's say you had miles per hour squared in here. So 0 to 3 is still a 3-hour period. change. Now I didn't use change here. This is net distance traveled. Technically we would say net change in position is technically a better way to say this, because this is the velocity function. So the miles would be the position function. X would be where it is, not how far it's traveled, but where it is. But if you take its ending position minus its beginning position, that gives you the net distance traveled. Okay, but distance traveled is not always bad. But remember, we said when you take a rate of change here, this is the net amount of change. So this would be the net change in position. This would be net change in, what'd you say? Velocity. That's right. And the units here would be miles per hour. So think of this as being like x double prime in here. And so this would be like x prime of 3 minus x prime of 0, correct? So it'd be like your final velocity minus your initial velocity. So it'd be the net change in velocity. So you actually could have a rate here, right? It's not like you couldn't, when you have a rate here, that it's not still a rate, right? This is the rate of change of velocity. And so this would be the net change in velocity. So it'd be your ending velocity minus your beginning velocity, okay? So it's still a net amount of change. It's just it would still be a rate, okay? So a lot of times people don't think about that. And it doesn't have to be about motion either, okay? This could be the integral, and let's say this was dollars per unit, and let's say this was P prime. P prime is in profit, right? So what would be, and let's say that was dx, x was the number of units. What would this represent? This would be the net change in profit. So it would be the profit in making 3 units minus the profit in making that. That's kind of weird, number of units, whatever. But this could be net change in profit, for example. So this would be in dollars. The units here would be in dollars, right? That kind of thing, okay? This, if you remember, that had a name. It was called marginal profit. Marginal profit was the P prime, okay? So it could be other kinds of units as well. All right. So anytime we have an integral, we have a rate of change, we want to find the net amount of change, this integral setting that up. So that is a real important takeaway from some of the things we've seen, and I think it came up in those packets as well, and it comes up a lot in the pre-response questions. Okay, here's kind of an offshoot of that velocity one we were talking about. If you do the integral of the absolute value of velocity, okay, so you might even think of this as x prime, whatever, but what's the absolute value of velocity? That's speed, right? Absolute value of velocity is speed. Okay, so let me write that up to the side. Speed equals the absolute value of velocity. Okay, when you do the integral of the absolute value of velocity, what's that give you? No, not net.
They're just
Total distance traveled. We don't even have to say net change. We don't even have to say total. It's not really even total change. I mean, I guess you could say total change. It's not really even that, because it's not really even a case of antiderivative. Now, what you do is, well, especially since 90% of the time we're going to get to use calculators, right? So we can type that in. We can type that in. If I took, I mean, let's do a quick little example here. So if I took the graph of x squared minus 2, let's do this. So let's go x squared minus 2. Okay. Now, let's say we were going to look at that from -2 to 2. Okay, we were going to do the integral of -2 to 2. What was that? X squared minus 2. Okay, so if we go back to the picture, now there is some, we don't hardly ever use this, but right here we could go integral, and I could put in my lower bound. I think I can just type in -2, and then type in a 2. I guess it won't let me just type in. So what was that? -8/3. So it'd be right about there. Right? Close enough. Okay. So the net distance traveled. So what would this tell you? The blue graph, let's say, was velocity. Let's say that was miles per hour, feet per second, whatever. Okay. So what would that tell you starting here? What would this tell you about what direction I'm going? If we're just going east, west, left, right. So I'm going to the right first, but I'm going slowing down, right? Slowing down. Right here I stop. Then I'm going back, west, 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 faster and faster and faster, right? Then still going west, but now slowing down, right? Slowing down, stop. Then I'm going to come back to the east, right? But I spent more time going west. So my net distance traveled was negative, right? So my net change in velocity was negative. Now, what happens when we put absolute value bars around it? What if we grab this and we take this, and I don't know if I can do this. I'm going to try to cheat here. See if I can, no, that's not. What was it? That's nice. Okay, so if you highlight something, hit the answer. I wasn't sure if I could do that. Okay, now what should happen? Okay, and compare that to, of course, we know this was -2.666 repeating. Okay, what just happened there? Well, what I did was, let's go ahead and graph this thing. Oops. Let's go ahead and graph this. See if that works up here too. God, that's awesome. Okay. Now look what we got. Right? What the absolute value do? It just took what was negative and made it positive. So now that area was all positive area. So now we're going to the right. Okay. And so that's a certain amount of area. So that's how far I've traveled. But when I turned around, instead of subtracting that area, right, it's adding on that area because now it's all positive. So now it's adding this area as I go this way, which is the miles. And then when I turn around, it's adding those miles on, right? So everything's positive instead of subtracting those, which you do in net. Okay? So by doing the absolute value of velocity, you flip this up to positive. It makes all that area positive. And you get the total distance traveled. Okay? So that is a very, very important piece of information right there. that's going to be useful when you do these problems, okay? Let's see, was there another one where we've used that? Not really. Not really. Okay. All right. Nothing really comes to mind right now. But again, area is the thing. But again, we can use rectangles if we're not using a calculator. Say, you better show up this morning.
Yeah, I was gonna show up earlier, but I kind of stuff.
All right, get your desk. Leave all your stuff here. So you get to use a calculator. Use your calculator. Use your phone.
Hi, Max. Morning. Max will be watching you.
No.
Oh, no.
Okay. All right. So what was I saying? All right. What I was saying was that a lot of the time we'll get to use our calculator. We'll set up a definite integral and we will just type it in, right? The calculator will decide what it's going to have to do. Okay. But if we're not using a calculator, or sometimes even if we are using a calculator and it says use 6 right rectangles, that's where you've got to write out your 6 right rectangles. Okay. And then you can use your calculator to add them up, but you'll have to write them out like we did on the quiz, okay, and evaluate them, okay? So when they say use 6 right rectangles to find the total distance traveled, they're not using rectangles to find the total distance traveled, they're using rectangles to do the integral. You have to set up the integral, right? That's a mistake a lot of people make on those problems is they get all confused. Well, how can I do rectangles to do the total distance traveled? How can I do trapezoid to do the average value? How can I do, you're not doing rectangles to do the average value. You're not doing rectangles to do the total distance traveled. You're doing rectangles to do the integral. You have to set up the integral first that gives the average value or that gives the total distance traveled or whatever. Okay, once you set up the integral, then you do your approximation or you do your fundamental theorem or whatever. Okay, so those are just ways to evaluate an integral. These are integrals that give us or find something for us. Okay? All right, so back to this. Nobody has any questions. You're ready to hand it in. Ready to hand it in and have it graded. Is that what you're telling me? What are the better recent questions?
Like
Which one?
part C's.
The part C. So a lot of them were similar type questions, what you're saying. So on the very first one, okay. So now some of this may be easier now that we just talked about some of this, but it says a model for the temperature is given by this, where T is in minutes and W is measured in degrees. Use a model to find the value of W prime of 18. Okay, so how do we find, W prime means a derivative, right? It says use the model, which means this, right? That's just a mathematical model. So, and then indicate units of measure. Okay, so when it says use the model, they're just saying use this equation. So Emily, I'm not sure of your question. So was that throwing you off?
Do the derivative of.
Just do the derivative of that. Now, Is this a calculator problem? My guess is with weird funky decimals and stuff like that, that's definitely a calculator. Just say that's the top. Use your calculator. So you can actually use your calculator to do that derivative, right? And we remember how to do that, right? So right here, right here. It's got a T in it or an X? T. And so what was that? Somebody read it to me.
72 plus 380 e to
So
negative
how much? 380?
380
80 e to the,
negative 0.036 t.
right? And then what do you want to do? You want to plug in a
18.
18. Now I think it would be a good idea. Now here's the calculator. Notice the calculator did it. It changes instead of e to the, what we would usually do is we go e to this and then kick out a negative 0.036. 72 would go away. Well, what they did is, remember, a power to a power you multiply. So they did e to the negative 0.036 and then to the t power. Well, this is e to the negative 3.036 right here. But so that's what they did. So all we have to do is plug in an 18. So you can grab this. Probably the quickest way on this one is just to delete that t and raise it to an 18. That's probably the quickest way. But you can do the vertical bar and do t equals 18, right? Do the vertical bar, so you just plug in an 18, and there it is, negative 7 point. Okay? And then that would be negative 7 point, what was that? Negative 7.156. What would be the units? Degrees Fahrenheit per minute. Does that make sense anyway? So that's all it is. Just do the derivative, put in an 18. So this is going in reverse of what we were just talking about. Here's degrees. You do the derivative, you got degrees per minute. Okay? When would the temperature of the pie be 300? Put a 300 right there and do a solve on your calculator. Okay? All right. So what else? They weren't all exactly like that, but you're right. They were. They gave you a table, and then they would also give you an equation. What about part D on this one? What is this? And then what was P here? P was the population. P was the population of Pine Grove over a 10-year period. So what is this? What is this integral right here? The average value of P. So it'd be the average population over that 10-year period. Okay? The average population. Because think about it. P is measured in people. So what would be the units? Forget the 1/10. And T was years. What would be the units on the integral of P? Forget the 1/10 for a minute. What would the integral of people be? No. That's the derivative of people. Huh? No. No. People years. Remember kilowatt hours? Think about it. The integral of the P function, what did we say the P function was? What were the units? What's the P function? What's the units? No. Read it in part C. People. What would this be down here? X-axis would be years. Make a rectangle. What would be the area of that rectangle? People times years, right? The integral would be people years. Now, the other way to think about that is right here. Remember, here's why, the reason I'm spending so much time talking about this today is to
put together what we learned in chapter 5 with this whole idea about the area and the Riemann sum idea. Because the dt is what? Where did the dt come from? When we're talking about rectangles, where did the dt come from? No, that's what it used to be, and it still is, respect to t. It's doing it with respect to t, but where did this come from? In the sigma. It's the width of, it's the delta x, right? It's the width of the rectangles. So what you have are people tall rectangles and years wide. This is people years. So this integral would be people years. But then what's the 110? Well, what's the 10, actually? That's why I like to have it down at the bottom. It's really 10 minus 0. What's that? That's years. So what you have is people years divided by years. And that's why you get average number of people, right? That's why you get the average number of people. That's why your units then on this ends up being just people, okay? It's the average population over that 10-year period, okay? But that's what that is. That it says explain the meaning of this expression in terms of population. It's the average population over a 10-year period, measured in people, okay? Because that's what we just got done talking about back here on this one, okay? So that's what they did right there.
Okay, would you ever have a function that would have been like people years, so like people years squared?
Not really, I don't think. I mean, it could be, no, probably not. I mean, could you? Yeah, but why? I mean, I can't think of an example. Now, if you had kilowatt hours, if you wanted average kilowatt hours, if you were doing something like that, kilowatt hours is actually a useful unit. And so if you had the integral, so if you had the average of kilowatt hours, it could end up being the integral of kilowatt hours. So that'd be kilowatt hours times hours, and then divide by hours, right? So that I could see that be a situation. But people years, I don't know.
I was just like wondering.
Yeah, in general, that'd be an example of where that might count. Okay. What else? 6C. Okay, so now you got a rate. Now we got a rate. Now we got centimeters per second. Okay. Now, okay. So let's talk about this. This would be good because, let's talk about it. Based on the values in the table, what's the smallest number of times at which the velocity of the particle could equal 20? Now, between 0 and 12. Okay, now it says this is a differentiable function. So what's that mean when it's differentiable? It's continuous, right? Differentiable means it's continuous, so it's connected. There's no jumps and gaps and stuff like that. So we know it's going to go from 37 to 17. Now it might go up above 37, down below 17, and whatever. We don't know it's going to go straight down to 17. But we do know it's not going to skip over anything. The intermediate value theorem tells us that you're going to hit all those values between 37 and 17. Now, it might hit some above 37. It might go down below 17. We don't know. But it's going to hit all those values in between, right? And it's also smooth. There's not going to be any sharp points. We can do the derivative everywhere. Okay, that's what that means. So, what is the smallest number of times the velocity could equal 20? Well, could it equal 20 in here? Yes. Could it equal 20 in here? It could, but we don't know. We want the smallest number of times it could equal 20. Doesn't it have to equal 20 at least once here? Right? Could be more, but we don't care. We want the smallest number of times. So it's got to be 20 once. Doesn't have to be 20 there. Doesn't have to be 20 there. Doesn't have to be 20 there. Doesn't have to be 20 there, but it does have to be 20 there. So 2. 2 is the smallest number of times that this thing is going to equal 20 centimeters per second, right? That's intermediate value thing. That's intermediate value thing. That's what we're talking about. There has to be one time where that could happen. And when it says justify your answer, you probably should mention it. It would be good if you mentioned intermediate value thing, okay? Maybe not necessary if you do a good explanation, but you should, and again, mention that it's differentiable and all that stuff. What's the smallest number of times that the acceleration could equal 0? What does that mean? What's the acceleration? Wouldn't that be the derivative of this? So that would be v prime. So that'd be the derivative of this. So what has to happen for the derivative to be 0? Since we know it's smooth, there's no sharp points, right? Every time it turns around, right, the derivative would be 0, right? Changes from increasing to decreasing. So would the derivative have to be 0 in here? It could just be going straight down, right? It wouldn't have to even go straight. It could be curving, but it would never level off because it could be going down, 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 down. But then what? It's got to come back up. So at that point it comes back up. It'll have to be, the derivative will have to be 0 one time there, right? And then up, 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 up. One time, right? Isn't there only one time it would have to be 0, the derivative? It's going down, 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 and then up, up, up. This graph could just be going down and up, okay? So it's got to be, the derivative's got to be 0 at least one time, but it wouldn't have to be more than that. It might be, but it wouldn't have to be. All right, C, find the average acceleration of the particle over the time interval 8 to 10 seconds. Show the computation that lead to your answer. Okay, average acceleration, that's like saying average rate of change. What did we say? Average rate of change is what? Average rate of change, you think what? Slope between 2 points, right? Well, their 2 points are going to be 8 and 10, and this is the rate of change because acceleration is the rate of change of these numbers. It is the rate of change of velocity. So that is simply 6 minus 1. So this would be v of 6, or excuse me, this would be v of 10. I did that wrong. It was 8 between 8 and 10, right? So Emily said f of b minus f of a, but it wouldn't be f in this case, it would be v, right? And this would be centimeters per second divided by seconds. Isn't that centimeters per second squared? Right? Centimeters per second. This would be acceleration. So 17 take away 6 over 10 minus 8 is going to be what? 11 over 2 centimeters per second squared. Right? And that is, better answer that, Will. Did you get the email about the cell phones?
Yeah.
Why are they just now deciding?
Well, some things happen. Again, we always have to do this stuff because people are stupid. Somebody's taking pictures in bathrooms again and, posting stuff and blah, 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 right? I mean, that's what's going on. Here, and it doesn't affect us because we don't do that very much, but I have gotten lights, and they're supposed to be kind of the honor system. Remember, if you leave the room to go to the bathroom, make sure you leave your phone here, take your name tag, right? That's basically mine. I know, my sitting's supposed to be in the hole or whatever. I'm probably going to get Doc. They're going to walk by and see Will. His phone. I'll say, hey, I don't care as long as he's got an A+ in the class, he's fine. Jeez. All right. Well, she knows you can get a hold of you because it's going to be handy, it's going to be available. If it buzzes, you're going to look at it. All right, so that's C. Really, Jesse? That's the one you asked about?
I would have thought it.
Yeah, okay, so why? What about the wording made you overthink it?
I just thought I needed the average value.
Yeah, that's a danger of the word average here. So we do have to make sense, because here's the thing. I was going to save this for another time. I don't know why. Okay, so Jesse's thinking he had to do average value. Let's talk about that right now. There is a connection between the average value of a function and average rate of change. Okay, so let's talk about where he got confused on that. Because when it says find the average acceleration on the time interval 8 to 10, if your function that you were given was the acceleration function, then that's exactly what you would do. Let's look at that a minute. I'm not sure everybody's following what I'm saying. All right. So, let's say you had an acceleration function. What would be the units of it? Miles per hour squared. And you wanted the average acceleration on the interval 8 to 10. Right? That would be the average value. What you would want to do is the integral of acceleration. Because remember, if we're doing the average value of f, we want f in the integral. So if you're doing average acceleration from 8 to 10, you need acceleration in the integral. Okay? Now let's think about that. And then you would go 10 minus 8, right? So what would the units on this be? So now you're going to just type this in your calculator most of the time. So this gets to what Will was talking about. What's the antiderivative of acceleration? Velocity. So this would be like v of 10 minus v of 8 over, right? Because so if this is miles, oh, I meant to square that. Okay, so that's miles per hour squared. So this is miles per hour squared. So this would be miles per hour over hours, which is miles per hour squared, right? So that's why this gives you the average acceleration. So if you had an acceleration function, you would do this. Now, what if you had a velocity function? And you wanted the average rate of change of velocity. Now, what is the rate of change of velocity? That is acceleration. The average rate of change of velocity is like asking for the average acceleration. Does that make sense? But what does average rate of change mean? It means slope between 2 points. So the average rate of change of velocity would be v of 10 minus v of 8 over see how they're the same thing? See how they're the same thing? Because if you do the antiderivative of this, you do f of b minus f of a, but then you're dividing by 10 minus 8. Well, right? I was always wondering if anybody was, I always wonder every year if anybody's noticing that when we're doing average rate of change. We're doing big F of B minus big F of A over B minus A. Isn't that slope? Right? This is another connection. Remember the fundamental theorem saying that the area function was the antiderivative? This is a great connection right here. This is actually sometimes called the mean value theorem for integrals. But because the mean value theorem for derivatives, the mean value theorem we learned is the slope between the endpoints or someplace in between the derivative is at, right? But this is the connection. So when you hear the word average, it could be one of these two things. It depends what function you're starting with, though. So if they had given you the acceleration function and said, find the average acceleration, then yes, you'd want to set up an integral. That'd be like average value of acceleration. But if they give you velocity and what the average acceleration is the rate of change of velocity. So they're asking for average rate of change. So they're asking for this. But again, you can get it by thinking, what do I want my units to be? If they want average acceleration, I want miles per hour per hour. Well, in this problem with centimeter, you were given velocity. If you go back to this packet, in this problem, you're given centimeters per second. Well, if you want average acceleration, you want centimeters per second. So you've got to take your velocities divided by your seconds. And so that's why that's rate of change. So there is a connection there. So maybe where you were stuck was you're like, okay, I need to do the average value, but I don't have an acceleration function to put into my integral. What was that?
I honestly don't know.
Yeah. There is a connection. There is a connection between average value and average rate of change, right? It just depends, I'm doing the average rate of change of what, right? I'm doing the average value of what, okay? So if I'm doing the average rate of change of velocity, if I'm doing the average rate of change of velocity, then I want to do slope of velocity. If I'm doing the average value of acceleration, I want to do the integral of acceleration, right? That's the key. So if I'm doing whatever function I'm doing the average value of goes in here. Whatever function I'm doing the average rate of change of goes up here. That's the key. That's the key. Okay? But there is that connection. So finding the average value of acceleration is the same thing as finding the average rate of change of velocity, because they're both finding acceleration. Okay, they're both finding average acceleration. All right, well, what the heck, let's finish this with part D, because this is important too. So it says, use a midpoint Riemann sum with 3 subintervals of equal length and values from the table to approximate this. So this is your simplest thing to actually give you the integral, but remember, a Riemann sum does an integral. What they might have said instead is, they might have said use a midpoint Riemann sum with 3 subintervals to find the average value of the velocity from 0 to 12, right? Well, then in that case, we would be wanting to do this, right? And we would do our Riemann sum to get the top part, but then we'd have to realize we have to divide by 12. But all they ask you for is just this. So do the Riemann sum, use this to justify. Well, okay, so since the nice thing is these are all equal subintervals, so we're supposed to do 3 subintervals. So that would be, 0 to 12. So that would be, so they'd be 4 wide, yeah, okay. So they'd be 4 wide. So we would go from here to here.
It's a midpoint.
Oh, it's a midpoint. Okay. So the width would be, let's just back up. So 12 minus 0 divided by 3. So we're looking at a width of 4. So probably better to just do it this way. So 4, 8, and 12. Right? Where's my midpoints in that? 2, 6, and 10. Right? So my midpoints are 2, 6, and 10. So I want this, and I want this, and I want this. Right? And so, can't go that way. But so I think it would be good of you to write V of 2 times 2 plus V of 6 times 2 plus V of 10 times 2.
Why times 2?
Oh, times, yeah, thank you. Yes, width is 4. Okay, now, would you have to write that? No, but you did have to write this. 17 times 4 plus 1 times 4 plus 17 times 4. It says show the work that leads to your answer, right? So at the very least, you have to have this. I think you should have this with your width. I think you should write it out that way too, I think, to be safe. But again, what would be the units, right? The units would be centimeters per second times seconds. So that's going to be centimeters, right? It's going to be centimeters, which we'd expect. So what is this? 76 plus 76, 152 plus 4, 156.
68, 17.
Oh, yeah, 34, not 38. 34 times 2 is 68. There you go, 68. Okay, so 136 plus 4, 140. So 140, and that's where you could use your calculator. If this is a calculator one, you can still use it, but you've got to write that out. And so this is 140, is that what we said? Using correct units, explain the meaning. So what would we say? The net distance traveled between 0 and 12 seconds. The net distance traveled between 0 and 12 seconds. right, sample 3. Sample 3.
We can have another homework.
What's that?
We have another homework grade. Next.
Yeah, that's about the last grade that's going.
Mine wasn't that.
I don't know. I'll be honest. Okay, what do we got? What do you got questions here? Look at this right here. I mean, right off the bat, number 3. What, maybe it was an easy one, hopefully. What'd you have? Nice thing about this is speed, right? We talked about that. What's the integral of speed? Total distance traveled. Now, they didn't ask that here, right? Or total amount of change. Now, it says the fuel consumption, so S, oh, I take it back. I'm sorry. My bad. S is speed is the input here, so that's different. That's different. So forget that. Okay, it's miles per hour, right, is the speed, but the units of C is gallons per mile. So when we do the thing here, okay, the common misperception is people would put gallons. I think that's wrong. Gallons is wrong. Why?
So the DS would be miles per hour. not just
Okay,
miles.
here's why. Well, okay.
Yeah, gallons.
Geez, a problem like this makes me rethink.
I mean, you just read it out like units. Just
Yes.
Replace everything with units and then just.
Absolutely. Now, but what I feel bad about though is this discussion we had here, right here. You know, I guess I should be more specific about this. See, and that's where this darn thing comes into play. You have to pay attention to that, right? Because typically this is rate of change with respect to, so this is miles per hour and this is hours, right? This is dollars per unit and this is units, right? And so when we were talking about, well, I guess I don't have it up here now. It was in that packet. We were doing people years. Remember we were talking, why is this people? Because the dx was years, the dt was years, and this was people. So the integral was people years, right? So the easy answer on this one is, what is the units on this? It is gallons per mile. What's the units on S? So the integral is going to be gallons per hour. Gallons per hour. And that is how you want, because again, what would this graph look like? The graph would look like gallons per mile. And the units down here, the S units, would be miles per hour. So our areas, right, when we do an area, it's going to be this times that. And it's going to give us gallons per hour. Okay, so it's going to be the net change in gallons per hour. So we do have, again, but I have said this many, many times, is the nice thing about integral problems and setting up integral problems is it's all about the units. What do you want the units to end up being? Or what are the units going to end up being based on what you have here? Okay. And so, I'm assuming sample 3, correct choice is C. Yeah. Okay. I was also going to look at number 5 here, because this is very similar to what we were just talking about. Particle moves along a straight line so that its velocity is given by this. How far does the particle travel between T1 and T3? Well, that is a total distance travel kind of thing, right? Total distance traveled, we said we want to do the absolute value of velocity, but here's the thing. What do you notice about T squared when T is 1 to 3? So it's positive, right? So we don't have to worry about the absolute value part of that if the velocity is positive anyway. Only if the velocity is going to go negative at all do you have to worry about the absolute value. Since it's going to be positive, it doesn't matter. So the integral of T squared from 1 to 3 is what we're looking for. The distance traveled from 1 to 3. Okay, so 1/3 T cubed, 1 to 3, put in a 3, 27/3 is 9, put in a 1, so that would be 8 2/3, which would be that one right there, right? So that is along the lines of what we're seeing. So we really want to now that we were done with chapter 5, we really want to be able to use that integral as a tool. And that's why I went through those things here at the beginning today. What can the definite integral be used for? We really want to use that integral as a tool now to solve these things. And this is why I said, I remember a while back saying when I was in high school, I always thought an integral and antiderivative were the same thing. They're not, right? And the antiderivative is just one way to do an integral, right? Like we did here. We did fundamental theorem part 2. Now, this is a no calculator problem, right? So that's why I did that, right? I could have just typed out my calculator if it's a calculator problem. So using the integral as a tool. So we used to be able to do antiderivatives, and so you probably could have done this way back when, right? When we were just learning antiderivatives, we didn't know anything about an integral, right? But now I think they're easier to do as integrals. And sometimes we'll still do it the way we did with antiderivatives, but sometimes we may not. And especially when we can use our calculator. Okay? What else? Including some old stuff here. If you got some questions about some stuff we learned before, I mean, that's definitely why I want these new packets. That's definitely one of the reasons I'm bringing in the new packets now, is all that stuff that was on our midterm. You know, it's going to be on the final. So we're learning this new stuff, but we got to go back and relearn and revisit all that old stuff before too. Equation of the line tangent to the curve at x equals -2 is y equals x plus 4. What is the value of k? Equation of the line tangent curve. Okay, so as soon as you read that, what do you think? What comes to mind? Should be several things. Derivative, right? Because that's slope, right? What else comes to mind? How do you write the equation of a tangent line? Right? Those are the things that should be coming to mind. Tangent line. We get the slope from derivative. Now, they've already told us right here, though, what the tangent line is. So what piece of information have they told us right there? What is that? Slope is 1. So when we do the derivative of this, it's got to equal 1. That's what they've told us. So how do we do the derivative of this? Quotient rule. So u prime v minus uv prime all over v squared. So u prime, derivative of the top would be k times the bottom left alone minus the the top left alone times the derivative of the bottom. What's the derivative of the bottom? 1, because k is just a constant, so it goes away. Okay, here k is in front. All over the bottom square. Now, what else can I do here? Huh? Oh, right. And I know that's got to equal 1. But what else can I plug in? Because I got too many variables. I got a k and an x. I can put a -2 in for x. So I'm going to get k times k minus 2 minus, and then -2k plus 8 all over k minus 2 squared equals 1. So I can multiply this over to that side, and I get k minus 2 squared, which would be k squared minus 4k plus 4. On this side, I would have k squared minus 2k, but then I'm going to end up with a plus 2k. So they're going to disappear, right? So I'm going to get k squared minus 2k plus 2k minus 8, right? So those are going to go away, so I'm going to get k squared minus 8. Now I can subtract the k squares from both sides. -8 equals -4, just 7 it is. So I got -8 equals -4k plus 4, -4k equals -12, k equals 3. There we go. Now, one of the things I look for when I'm grading these packets, right? One of the things I look for is when I get to a problem like this, and so I pick out some random problems, right? So I pick out some random problems, not necessarily random, ones I know there should be a bunch of work shown for, right? And so when I get to one like this, I know that if somebody's just got the answer circled here, they didn't do it. And they just, whatever, circled the answer or copied it from somebody over there. Now, you can still copy all the work, but I figure those people that are copying are too lazy to even copy the work, which happens a lot. But if you're not too lazy, you can get those points anyway. So, anyway, remember what I said, on the multiple choice, when we actually take the test, you don't have to show work. But, for the multiple choice part, but on these review packets, you do, especially, even in the calculator ones, right? We said the calculator ones are certain things you can do on your calculator. But, you can do the derivative, you can plug in, you can solve an equation, but you got to write the equation out that you're solving. So if you're doing a max problem, local max problem, or whatever, do the derivative, set it equal to 0, then you can use your calculator to solve it, that kind of thing. Okay, well, we'll just continue this for tomorrow. These 2 packets, let's be working on those. Get into the free response parts as well would be good. I don't know, let me look at the free response. A lot of that we can do now, or we're getting closer anyway. Let me just read through this. Number 1, you've got a velocity, speed, acceleration, so that's derivative stuff. You can sketch, is it velocity increasing? Find the distance a particle travels, so we just talked about that. The distance, that's like total distance, so we just talked about that being an integral. Number 2, look at this, sand is being poured in and then being removed, so we've talked about those kind of problems. What do the units mean? So an integral might get involved there. This is a differential equation one. We haven't done any of those for a while, so that's kind of an interesting one. Here we got this area you wouldn't be able to do yet because it's kind of in between some different curves. But equation of tangent lines, stuff like that. It's kind of it looks like a Shanghai kind of thing, right? You got this tangent line, you can do the derivative, the derivative here is going to be the slope of that line, the derivative here is going to be the slope of that line. So 2 different ways to do slope is kind of your Shanghai situation. Here you got a function, it's a lot of chart questions, local max, local min, where's it concave up, right? That's good review, chart kind of stuff. And then here's an area function. So we know G is what? What did I tell you guys? When you see a problem like this, what's the first thing you should write down? You see that, what's the first thing you should write down your paper?
Big F.
No, wouldn't use big F here.
F prime is equal to
Close,
Big G.
it's backwards. G would be, if you want to use big F, G would be the same as big F, right? I mean, but what does big F mean? Yes, in our class, we use big F to mean antiderivative of little f. And that's pretty universal, but it's really the derivative symbol we want to use. So therefore, G prime would equal, that's what you want to write. That's what you want to write. Because all of these questions, if you notice, the graph they give you is F. All of the questions are about G. Now, they did say the average value of F. That's the only one. But the rest of the questions are all about G. So if you're going to answer questions about G, but you're going to reference the F graph, that's no good unless you've connected the G and the F graph. That's why you write this right here. See, they've connected them here, but you have to give that. And so G prime is equal to F. So if you're talking about where's a local max of G, or an inflection point of G, it's when G double prime changes from positive to negative. An inflection point, that's like saying that's where F changes from positive to negative. So here and here, here and here, right? That's what you would be looking for inflection points. But, so this is important. When you see that, you make that connection. Okay? So let's keep working these packets. We're going to get started in chapter 6 tomorrow.